Hello everyone. Our group conducted Lab 13 AC Impedance. Our group member is David So, Jaeeun, Jaeeun, and Allison Oh. In this experiment, we study how resistance occurs in an RLC circuit and how it maximizes current and power. Now let's look at our objectives. In this lab, we study how a series RLC circuit changes with AC frequency. Using the Pascal A50, we measure voltages on the resistor, inductor, and capacitor. We find the circuit's impedance, phase angle, and power, and compare the resonant frequency with theory. This helps us understand how R and L and C work together in AC circuit.
Electricity can flow in two main ways, the first being DC, direct current, and the second one being AC, alternating current. In AC, voltage and current changes with time and there is frequency, so we can't use Ohm's law of V equals IR. We need impedance, which is in units of ohms and refers to the total opposition to AC current. It also takes into account the reactances of inductors and capacitors. The two equations above describe voltage and current as sinusoidal signals in a circuit. The 2 pi radians is equal to one full wavelength of 360 degrees, and the 2 pi f is called the angular frequency and is in units of radians per second, telling us how fast the wave cycles. We also see the symbol for the phase angle, telling us how much the current is shifted in time compared to the voltage. Inductors resist changes in current while capacitors resist changes in voltage. Inductive reactance increases with frequency, so inductors block high frequencies and pass low frequencies. Capacitive reactance decreases with frequency, so capacitors block low frequencies and pass high frequencies. Inductors follow Faraday's and Lenz's law, where changing current induces an opposing voltage. If current rises, the inductor generates voltage to oppose it. If current falls, it drives current to maintain the flow. Speaking of resistance, when you take a look at this graph, you see how voltage and currents are not in sync. For the resistor, the voltage and currents are in phase. For the inductor, voltage leads the current by 90 degrees. For the capacitor, current leads voltage by 90 degrees. This goes back to how inductors resist changes in current, while capacitors resist changes in voltage. Now, when the two values of XL and XC are equal, there is what is called resonance. At this point, impedance is equal to resistance and the current reaches its maximum. In a series RLC circuit, the voltages across each component have maximum values called amplitudes, which show the peaks of the sinusoidal waves for each component. To find the total voltage, you can't simply take the sum because voltages are out of phase. Using the Pythagorean theorem is a better way for solving for V total. And that gets us to this first equation, which can be rearranged to a second, even longer equation. The 2 pi f we spoke of earlier from the sinusoidal wave is significant because it tells us how fast the AC cycles, which directly affects XL and XC and therefore total impedance of C. We also have what is called the phase angle, which tells us whether a circuit behaves more like a capacitor or an inductor. A positive theta indicates that the voltage is ahead of the current and therefore the circuit is inductive. A negative theta indicates that current is ahead of the voltage and therefore circuit is capacitive. In DC, power is simple. We just have P equals VI. But in AC, this phase angle is used in the equation shown for P equals VI cos theta. The purpose of activity 1 is to measure the internal resistance of the induction coil using Ohm's law in a series without the capacitor. The purpose of activity 2 is to measure voltages in the RLC circuit and observe the phase relationship between voltage and current. The purpose of activity 3 is to calculate the circuit's power value and identify the frequency value to compare it with the theoretical value.
As you can see in the picture, in our experiment, we used the Pascal 850 interface, resistor, and an inductor, a capacitor, and also we used a multimeter for measurements. In method section, the formulas used in each activity are shown on the screen for reference. In activity 1, we built a simple series circuit with a resistor and an inductor. We measured the voltages across the resistor, the inductor, and the entire circuit. From the resistor voltage, we calculated the current, then found the part of the inductor's voltage caused by its internal resistance. Using these values, we determined the inductor's internal resistance, which we used for the rest of the lab. In activity 2, we added the capacitor to make an RLC series circuit. We measured the voltages again, calculated the current. We found the phase angle between the total voltage and the current, then compared it with the theoretical value. In activity 3, we calculated the real power in the circuit using two different ways. Then we changed the frequency while keeping the voltage the same and looked for the point where the resistor voltage was the highest. That frequency was our experimental resonant frequency, and we compared it with the theoretical value from L and C.
Hello, my name is David So, and I'll run over some of the results that we found in this lab experiment. So for activity number 1, we tried to find the internal resistance in the induction coil, and this is for better accuracy and preciseness of the measurements for activity number 2 and activity number 3. So we calculated the internal resistance using this diagram, and this diagram basically works because in theory, we know that the voltage of the inductor is 90 degrees faster than the current, while the voltage of the resistor is in line with the current. So through measuring voltage of the total circuit, the voltage of the inductor, voltage of the resistor, we found the voltage of the internal resistance to be 0.27 volts. And utilizing V equals IR, we found the internal resistance is about 8.6 ohms. For activity number 2, we tried to measure the phase angle between total voltage and current. And we also utilized this diagram because we know that the impedance of the capacitor is 90 degrees slower than the current, while the impedance of the inductor is 90 degrees faster. So utilizing the values, measured values, the given values of 8.2 times 10 to the negative 3 henries and 1 times 10 to the negative 6 farads, we found a theoretical data of negative 44.87 degrees. And through utilizing same diagram but in voltage, we found data to be negative 41.96 degrees, which is about 6.5% error, which suggests that it is pretty close and accurate. For activity number 3, we compared the power using two different equations, and these have 3.9% differences, which is pretty accurate. And also for our last activity, we tried to find the resonant frequency, and we found that theoretically using this formula right here with the given inductance and capacitance, and we found the theoretical value of 1757.57 hertz. And experimentally, we tried to find the frequency with the highest voltage, and this is because at resonance, the impedance would be the lowest, which means that the current of the circuit would be the highest. What that suggests is that the voltage would also have the highest amplitude at the resonant frequency. So if you look right here, you can see that at 36 hertz, it's at the highest voltage amplitude. So we found the resonant frequency of 1736 hertz. And this have about 1.23% error, which suggests that our data is pretty accurate. So in conclusion, our data is pretty accurate and precise. It proves the theory of the phase angle and also the resonant frequency. There are some possible errors, which includes inability to measure the inductance and capacitance.
In this experiment, we studied resonance. A common example is wireless charging. When the pad coil and the phone coil share the same resonant frequency, XL equals to XC, impedance is low, current increases, and VR peaks just like in our lab. From the power formula, P equals to V total times I times cosine theta. As theta approaches 0, the power factor approaches 1, delivering more real power. So what we learned isn't just formulas, it's the exact principle modern wireless power system use. That's the end of our presentation. Thank you for listening.